knew, and I called her Cat for the longest time.
You're out of the way.
I should have candy or something.
Bro,
It's actually straight beer.
All right, here, folks.
I'm bringing in the next show. That was so funny. Primal habitat. I feel like my whole life, bottle.
I'm going to start with your homework quiz. So you guys will need your tablet because it's going to be done in through the MyAP. Multiple choice questions. There's 5 of them. I'm going to put up a timer for 10 minutes. You can go past the timer, but I want you to start getting a feel for like the pace in which you should be able to work at to complete these questions. The per question pace for the no calculator section is basically 2 minutes a problem for the multiple choice. So just to give you an idea. So if you go into the MyAP, you should see a assigned quiz or whatever it's called, titled S2 HWQ number 1. So you should see that in there. Looks like some of you have already started it. Oh, I see what's going on. I need to fix that. I'll do that. Never mind. Some of you haven't started it.
This is no calculator,
right? You can have a calculator out. I don't think it'll help you at all.
Okay.
But like, I'm not worried about that right now.
Yeah.
You probably want a separate sheet of paper to write some scratch on. I would have a hard time doing some of these things in my head in entirety, so I'm sure that you want to write some stuff down. Once you're in, go ahead and start. Like, don't wait for me. I'm just gonna put up a timer here for you guys. I want to mute this. Okay, that was way louder than I wanted it. So there's the timer going. Again, if you exceed the timer, don't worry about it. I want to just, eventually we'll worry about timing, right? Like eventually I'll put like a hard clock on these things, but like not the first one, not the first few. But I want you to start being mindful of how long you're spending on stuff. You know what I'm saying? I'm going to shut it now so you can think. Sorry. Yes. Yes, there's a stack on my desk. You're welcome to it. You're welcome. Yeah, of course. Yeah, help yourself. I don't think it'll, you might have to submit at the end, like once you've got it back up and opened or whatever, but that's fine. I don't think I put a time limit on this or anything where it's gonna like time you out. So we just passed 10 minutes. Again, if you have a little bit more to do, that's fine. Like the 10 minutes not a hard deadline, but I want to start putting clocks on these things and getting you guys to be mindful about how long you're taking to do stuff. So we'll take another 5 minutes here or so to finish up. Just as a heads up, for those of you that are continuing to or have finished, we'll start on the related rates practice sheet that I gave you guys last time. We'll start with here in another 5 minutes or so. Give everybody a chance to kind of finish things up. I know I just restarted the 10-minute time. Let's just stop for 5 minutes or so. Wasn't worth the switch for another one. Yeah, it looks like the graphic ones are going on. Yeah, crunch some numbers. Catherine. I think. My friends are smiling like I'm not sure that's true.
I just did it once. I turned it on once. I didn't do it.
Okay.
Oh no, it's not working. Hold on, I can retry.
Yeah, just try submitting again. Good to know. All right, here, folks. Close enough, I think. So let's take a look at these related rates problems here. You're still kind of keying in the end of your answers because you have to resubmit, no problem. So let's take a look at these guys. So I'm gonna read through the solutions, and then if there's stuff you want to see done afterwards, we'll do that. Sound good? So number 1. Our answer is -1/12. I think meters per second should be the unit on that. Number 2 is 60 pi centimeters squared per second. If you wrote that as a decimal, that's okay. You know, like 180 something or whatever. Number 3 should be 20. I guess that's units per second because they didn't give a distance on that. And then number 4 would be like -4 degrees Celsius per minute, or I think it's minute. Yeah, okay, minutes. Okay, so those were the answers. -112 was the first one. What was the second one? Negative or positive 60 pi. Again, if you wrote those as decimals, that's fine, right? Like, no big deal. I didn't have a calculator next to me, so I just did it exact. So I had things in terms of pies or whatever. All right. Questions on those? You've read through answers. Are there things you'd like to see done? Sam? Number 2? Sure. So it says the area of a circle is given by the formula A = pi r squared. The radius of the circle is increasing at a rate of 3 centimeters per second. Find the rate which the area is changing when the radius is 10 centimeters per second. So the directions I gave you at the top say we should draw a picture. And when I'm doing these, probably at least while we're still trying to get a handle on them, to try to draw like an illustrated picture of what change is happening. So here, the circle's expanding, so I drew like my circle. And the reason I'm going to do it this way is that the next question it asks to write the equation to describe the situation. Well, it told us in the problem it's going to be area equals pi r squared. And now I ask you to go through and look at the the parameters in that equation, decide whether these are changing with respect to time or they're constant with respect to time. If I look at my picture, well, the radius got bigger, so that's a variable. And the area got bigger, so that's a variable. It's okay. And because these are variables, when I differentiate with respect to time, I know I'm going to get a dA dt and a dr dt. It's okay. So I've figured out what's a variable, what are the necessary rate variables, and obviously pi is a constant. I'm not going to bother to write down that pi is a constant because I think at this stage of the game everybody's pretty comfortable with that. Next, I want to write down what's given to me. So it says the radius of the circle is increasing at a rate of 3 centimeters per second. So that's telling me that dr dt is 3. And I know it's positive because it says increasing. And then we're asked to find the rate at which the area is changing when the radius is 10. So I know that the radius is a variable. So r equals 10 is not like something, but rather a parameter on that dA dt, right? It's asking for the rate to which the area is changing. That wants a dA dt. When r is equal to 10 means that I'm going to plug 10 in for r after I differentiate. Because I'm looking for the change in area at that particular instant when r is 10. Does everybody feel so far so good? Okay, the next step I ask for us to do is to determine if anything needs to be eliminated. So typically all I want to do is look at my rate variables that I'm going to generate. I have a dr dt, I know value for that. The dA dt is what I'm looking for, so I'm good. Nothing needs to be eliminated because I have all the rate variables I need in order to do the problem. Is everybody good? Now we'll go ahead and do our implicit differentiation. When we do that, we get dA dt equals pi times 2r dr dt. Everybody's cool with the differentiation that happened. Now it's just time to plug things in. We know we're looking for dA dt when r is 10. So I can plug in 10 for r, and we're given dr dt is 3. So we end up with 65 or 180, whatever the extra numbers are at the end. There's probably some ones there. 181 or 187 or something. 188. I don't know. Pi times 60 in my head, which is a great deal of accuracy, surprisingly enough. 188.4. 188.4-ish. Anybody do the decimal? How'd I do? That's Sam, are you happy with what I did? So again, notice how long I took in the beginning before I actually started to do any calculus, right? I spent the time drawing the picture, making sure things were labeled intelligently, deciding what's changing and what wasn't. What rate variables are going to be generated? Do I have the information for the rate variables that are going to be generated? And only after I've done all of that did I bother to start in the calculus. You dive in too quick, and you will miss if you need to eliminate a variable. You're going to get jumbled on like how do I use the information that I'm given. So much simpler if you spend that time early on and like draw your picture. Determine what's a variable. What are we given? What do we need to eliminate to make the problem doable? And only after you've gone through and done all those checks do we differentiate and plug in. Actually, 188.4, I did pretty good. 0.4 now. Yeah, to get me to the hundreds was it's unreasonable expectation. Go. Any others from this set that you guys want to look at? Overall, did this go okay? This felt reasonable. That these problems were like, okay, I can handle these. This should have been stuff that you could do fairly comfortably. I have your next set here. So again, I told you I think I have 4 of these that are going to get kind of progressively more complex as they go. So if that first set of problems wasn't much of a challenge, that's great. You're in a wonderful place. This next set will be a little bit more challenging, and the next set a little bit more challenging after that. The last set may be the most challenging. I don't know that there's really much difference between sets 3 and 4, but and then yes, sure. So again, this sheet that I just passed you, you should have ready for next class. We'll do the same thing. We'll read through answers, take questions. I assume the next go around we'll probably want to do more than one of these things. Probably be more than one question. I might ask you guys to if you have the question, okay, let's come up and write down what you did, and we'll talk about where we got stuck at or where we got turned around. Or it's I thought I did this right and get the right answer. Might invite people up to show what they did and talk about where the mistake is and how to figure that out, just so we get more comfortable with these problems. Okay? Everybody feel so far so good? Before we dive into new things, does anybody have questions from 4.9 that they want to ask about? I know that most of us probably are not finished with that, and that's fine, but Ava? 15? Sure. Let's see. Okay. So it asks us to find the general antiderivative here. So the way it's currently written as a quotient, I don't want any part of this. Antiderivative of quotient is a nightmare problem for me. So what I'm going to do is, before I start trying to do the antiderivative, I'm going to do some algebraic manipulation to make this problem considerably easier for myself. Everybody go to the plan? So the first thing that I notice is that the denominator of this fraction is a monomial. So I'm just going to break this fraction that has one common denominator into 3 separate fractions, each with their own separate common denominator. Is everybody okay with that? So far, so good? Still fractions, still don't love that. So next thing I'm going to want to try to do is to rewrite these as each of these as a power function. So I know that the square root of t is just t to the 1/2. And if I use my exponent properties, I can do that. Does everybody feel good to where I've gotten to here? This now is super manageable for me. Since each of these are just a power function, I can just use my antiderivative rule for a monomial to deal with each of these. So finally ready to do my antiderivative. So to do the antiderivative of t to the 1/2, or sorry, t to the negative 1/2, I'm going to add 1 to the exponent and then divide by the new exponent. To do t to the positive 1/2, I'm going to add 1 to the exponent and divide by the new exponent. And t to the 3/2, I'm going to add 1 to the exponent and divide by the new exponent. Feel good so far? Okay. Let's clean this up a little bit. So negative 1/2 plus 1 is 1/2. And 1 over 1/2 is 2, right? Wait, feel good? 1/2 plus 1 is 3/2. 1 over 3/2 is 2/3. Yeah, just the reciprocal, right? Everybody doing good? And then 3/2 plus 1 is 5/2. And 1 over 5/2 is 2/5. And the last thing I need on this is plus. I guess I should write it here. So, as long as I get it at the end. And that's perfectly acceptable answer. Does that feel good?
Yeah.
So the trick was doing the algebraic beforehand and getting that into a manageable state, because we have no antiderivative rule to deal with a quotient. The only one we have is 1 over x. It's the only one we have an antiderivative rule for. If it's any other quotient, I got to do some algebra to get it into something manageable. At least until we build out some other techniques way later in the semester. But that's like a whole, maybe like the most difficult antiderivative process is dealing with, like, how do I do the antiderivative of a quotient? And there's only certain quotients that will actually ask you to do. Certain types of quotients. Okay. Others from 4.9. That's a good one to ask about, right? Because you couldn't use the antiderivative rule at first glance, and you're probably like, ooh, what do I do with this? None of the rules seem to apply. It's like once you see the trick, it's like, oh, I can do that. Now that I realize that's a thing that can happen, like I can put that in my toolbox and use that if I get stuck, or look for that to make my life easier. Okay. We can always circle back. You know, next class we'll ask about homework again, and if you have more 4.9 questions because you got further along into the 4.9 homework, that's fine. You can always continue. Today we're going to talk about 5.1. So over the next couple of lessons, we're going to be talking about the area under the curve of a function. And somewhere along the line, we're going to connect that back to this antiderivative process. So, as a little start, we know that if we take the derivative of or of a position, we get velocity, and the derivative of velocity is acceleration, right? And then if I can do the antiderivative to kind of go backwards, right? So let me ask you a question here real quick. You're in a car going 50 miles per hour. You ride in it for 2 hours. How far did you go? 100 miles, right? So if you started at position 0 you're ending at position 100, right? So somehow that is related, that process of taking my rate times multiplied by time, giving me distance, is related to an antiderivative, right? Is everybody okay with that? Because we're now talking about position. So if I think about that as a graph, say this is velocity on the y-axis and time on the x-axis. So if this is like 50, and this is like 2. When I did 50 times 2 equals 100, what did I actually calculate also? The area under the curve, right? Is okay with that idea? So somehow this area under the curve is going to be related to this antiderivative process. Like somehow, like, because displacement is related to position in some way. We're going to marry those two ideas together in future sections, but I want to justify like why all of a sudden we're talking about antiderivatives, and now we're talking about the area under the curve. Like, what's the relationship here? Why change in years? We're building some intuition, like, okay, these two are related in some way. I don't really understand how yet, but I can see there is a relationship going on here. Does everybody feel like well justified in why we're changing gears to here? Okay. So finding the area under a curve like this, where the curve is a horizontal line, yeah, piece of cake, Mr. Kulik, I can do that. What if it's in general? Like your curve is some crazy looking thing, your endpoints are like arbitrary values, A and B. Not entirely clear how I would go about doing this, right? This looks like a nightmare. So before we try to attack this in the most general sense and look at the area under like any curve between any two x values, let's get specific and worry about doing this for a specific function that's not, a straight line first. Are you good with that plan? So let's consider the function y or f of x equals x squared on the interval from 0 to 1. Okay? So that's this graph. And we're going to look at the area under the curve. So that's that shaded region that we've labeled S. So initially, you look at this and you're like, well, this isn't much easier than the previous problem, but at least it's specific, right? Like the f is a specific function, the a and b are 0 and 1, like it's a specific area. That has a numeric answer. I can at least start like working towards an approximation of this. So if you're doing that, the first thing you might want to do is find a bound. So like, what two numbers does S have to lie between? Well, the lower bound should be easy. 0, right, is a decent lower bound to start because clearly there's something in that area. The area is not negative. And if I look at this, it's a square, right? What's the area of that square? 1. Is S bigger or smaller than the area of the square? Smaller. So clearly, like, S is between 0 and 1. Everybody's good with that? You might be able to do a little bit better and say, like, okay, if I draw the diagonal, that lower triangle should have area of a half. So S should be between 0 and a half. But getting much past that, I don't know, right? Like, it's getting a little bit trickier, right, to see what we can do for an approximation. So what we will do is we're going to divide S up into some strips. So what if I cut up S into, like, say, 4 strips? I'm going to label those as S1, S2, S3, S4. Everybody's okay with that? Now, those strips, finding the area of those, is not really any easier because they still have a curved spot on the top. But at least the 3 other sides are, straight lines. So I can approximate the area of each of these strips and then add up those approximations and get another approximation for S, right? So what I can do is I can just say, okay, well, what if I just take these strips and make some rectangles out of them? Okay? Everybody's okay with that idea? And can I calculate the area of those rectangles rather easily? Yeah, because it's just base times height, right? So the base is always the same for each of them. And the height here is equal to, the y coordinate of the function here. Everybody's okay? So we do that. Is this estimate going to be an overestimate or underestimate? It's an overestimate, right? Because the area of those rectangles is clearly bigger than the area under the curve because they overlap the curve. Okay? What if we went and did the opposite? So here we started with the right endpoints. What if we used like the left endpoints to draw these? Yeah. So if I do that, I might call these L1, L2, L3, L4. That's going to be an underestimate, as Anthony just mumbled. So what I've done now is I've just found a tighter bound for S, right? If I take the underestimate from the sum of L1, 2, 3, and 4, and the overestimate, the sum of R1, 2, and 3, and 4, S has to lie somewhere in between those. Everybody's good with that? How can I make that bound even tighter? More rectangles is exactly right. What if I just cut S into more strips and use more rectangles? Right? That'll reduce the amount of overlap in each case, and I'll get a more accurate estimation. That bound will tighten up even better. Does everybody feel good on that? Let's draw a picture to let you really see it. So what if I use like 8 rectangles? You can see I have less error in each of the estimates, right? The amount that I'm under S is smaller for my underestimate. The amount over S is less in my overestimate. So I've tightened that bound even better. Does everybody feel good? Okay, who sees where we're going? How many rectangles do I need to use to get exactly? Infinitely many. Yes. Yes, that's exactly right. That's exactly where we're going. Okay? So if I just take S and I cut it to infinitely many strips, and I calculate the areas for the rectangles that I can make from those infinitely many strips, the area of those rectangles will be exactly the area of S. That's where we're going. Okay. Before we do that and build out that formula, let's calculate some of these approximations so we get used to the notation that's involved and like what exactly things mean. It gets confusing if you haven't worked through a specific and we jump straight to the general. So you okay with that? So I'm going to scroll back here and just look at this guy. Okay. So if I'm looking at R1 here, the base of R1 is 1/4. Everybody agree? The height of R1 is going to be would be like f of 1/4, right? In this case, f of x was x squared. So we could write it as 1/4 squared. I'm just going to write it as f of 1/4. Is everybody okay with that? Okay. R2. What's the base for R2? Still 1/4, right? 1/4 to 1/2 is 1/4. And the height then is f of 1/2, right? Good. And then R3, 1/4 times f of 3/4, good. And then R4, 1/4 times f of 1. I'm going to write it as 4/4 just so it's a little bit, because we're going to try to generalize off of this now that we've done it specifically. Does everybody feel good about what we did here? Okay. So this 1/4 is the same in each of these steps, right? The base is the same every time. How am I finding the base? Why is it 1/4? Well, it's not the x value, right? The x values are 1/4, 1/2, 1/3, and 1. How am I getting that 1/4? It's what? That's the heights, is the x values plugged into the function. So it's the length of the interval divided by the number of rectangles that I'm splitting it into, right? Does everybody see that? So in this case, it's like 1 minus 0 divided by 4. Or more generally, okay? I'm taking that interval that we're finding the area over, and I'm just dividing it into n segments where n corresponds to the number of rectangles I'm going to use. Feel good? Okay. Now, what's changing in each for each rectangle? The heights, and what part of the height is changing? The x-coordinate that we're plugging into the function, right? We're still using the same function every time, but the x-coordinate we're plugging in is changing. It's gone from 1/4 to 1/2 to 3/4 to 4/4, right? So why is it changing? So we started at 0, and we took one step, and that's my new x-coordinate that I'm plugging in, right? And then we started at 0, and we took 2 steps, and that's the next x-coordinate I'm plugging in. Or we started at A, and we did 3 b minus a over n's to get to my third x value. Or we started at 0 and took n b minus a over n's to get to my last x value. Does everybody kind of see what I'm saying here? So this guy is like f of 0 plus 1 times 1 minus 0 over 4. And this guy would be like f of 0 plus 2 times 1 minus 0 over 4. Is everybody okay with seeing that? So it's like starting point plus 1 step, starting point plus 2 steps. The next one will be starting point plus 3 steps, and so on and so forth. Do you see how this is changing? And we're going to then sum that feel okay with what I just built? You guys remember the summation notation from last year? What's the name of this symbol here? Anybody remember the name of it? It's like one of your favorite hip slang words from a year ago. Yeah, sigma. Right? What is the I down there and underneath the sigma? What is I representing? Well, that's the index variable. That's going to be the thing that's changing in the sum, right? So we call that like the index or the index variable. And equals 1, it tells you the starting value of our index, and the n is the ending value for the index. So we're going to have one of these when I is equal to 1, plus one of these when I is equal to 2, plus one of these when I is equal to 3, plus all the way out till one of these when I is equal to n. Does everybody feel okay on what we just described? You're good with this? Okay. So this is calculating the area for n rectangles. An arbitrary n, but a finite n. How many rectangles do we need to actually get the area under the curve? Infinitely many. How do we turn this into infinitely many? Just use a limit. So we stick the limit as n goes to infinity in the front. Yes. Of course. Yeah. So this is for right endpoints, right? Because what we did here when we drew these rectangles was the right endpoints. Everybody's okay? How's this formula going to change if we did left endpoints? Let's write out this. Everybody's good? Let's do this first. Does that sound good? Probably best. So the base is 1/4, and the height is, well, it's going to be f of 0, right? Because we want to write it using function notation. Because we want it to be general, not just for this specific example, but we want to like take this pretty specific thing and try to generalize it out a little bit before we go jump all the way to the thing that we just wrote a second ago, which coming up from scratch with no specific example to look at, ooh, doggy, that's a big ask. All right, next rectangle is 1/4 times f of 1/4. And then 1/4 times f of 1/2. And then our last one is 1/4 times f of 3/4. You feel okay? Yes.
You might have explained this earlier.
No, go.
What does the 1/4 in front of each section? Where does that come from?
So we're just doing base. That's right here. Base times height, right? So the base is 1/4, and the height is f of, in this case, 3/4. Does that feel okay? Good. So let's compare this for my left hands with this for my right hands. They both have 4 rectangles, right? What's the difference between those? It's really just the starting value and the ending value, right? The left hand starts at 0 and ends at 3/4. The right hand starts at 1/4 and ends at 4/4. Did you see that? With what the x that we're plugging in? But like, like they both have one of those. Oops. They both have one of those. They both have one of those. Right? The only thing that's different is one rectangle. Well, I should say one area. I mean, they're different. They're all different rectangles, but one of the areas of the rectangles is different. Is everybody okay? So instead of taking one step, starting at 0 and taking one step, we need to start at 0 and take 0 steps. And then take one step, and then 2 steps, and then 3 steps, right? So the only thing that's going to change is instead of I, we want I minus 1. That means the first will be 1 minus 1, that's 0. The second will be 2 minus 1, that's 1. The last one will be 4 minus 1, that's 3. That's what we want to have. So let's just rewrite that for left. Again, that's the only difference in the summation between the left-handed point and the right-handed point. Is that okay? Can I move or rewrite it? I don't want to move it. You guys are copying stuff. I understand. I'm trying to not go too fast here. If I start going too fast, holler at me. Or if you have a question about hey, I don't understand where something came from, stop and ask. If you have a question, somebody else has the same question. I promise you. So we just did infinitely many rectangles. So if we go back to our arbitrary curve from A to B, we take the length of our step. That's the distance between each of the strips. That's the base of our rectangle. Textbook calls that delta x, which is the b minus a over n. Is okay. And then so that distance gives us the subintervals that we're working on. So a to x1, x1 to x2, x2 to x3. They called xa, they turned into x0, and b they turned into xn. And they did that down here. Is okay. Each one of these subintervals is going to represent the base of our rectangle. That's good. Then what we are going to do is describe how to find each one of these endpoints of our subinterval. So the first endpoint is starting at A. We take one of these steps. The second endpoint is going to be starting at A, and we take two of these steps. The third endpoint is starting at A, and we take 1, 2, 3 of these steps. Does everybody feel okay with what we've drawn here? So if we looking at xi, we're starting at A and taking I of those steps. And remember that delta x is just that b minus a over n. And this is exactly what we wrote here, right? Okay? So again, I'm just trying to marry the textbook's notation to what we did so that when you look at this, the formulas in the book, it matches what we did in class. That's all we're trying to do right now. Yeah? So far so good? So we build our rectangles. Each of them have the width of delta x, or b minus a over n. So my area under the curve is going to be the limit as n goes to infinity of n, this curve split into n strips and then make n, infinitely many rectangles. So the area of each of those rectangles is going to be the width, that's the delta x, times the height. That's going to be the right-hand endpoint of the subinterval. So x2, the width, times the height of x at x2. All the way down until we get to the last subinterval, the height of xn, or the height at xn. Does everybody feel okay? So this is using right endpoints. If I use left endpoints, and I still make infinitely many rectangles, do I still get S? Yes. If I use the midpoint of the subinterval instead of the left end or right end, and I add up infinitely many rectangles, do I still get S? Yes. If I use an arbitrary x value, that could be the same, but not necessarily, as long as it's inside each subinterval. And I take infinitely many rectangles using an arbitrary value from the subinterval. Do I still get S? Yes. Now, in practice, nobody's going to take arbitrary x values to do this, but you could. In general, you'd use, the left end or right end or midpoint, because calculation is easier if you're going to make an approximation. Blah, 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 blah. Don't care about that. We talked about that. Let's look at these two examples. Says let A be the region, or the area of the region that lies under the graph of f of x equals e to the negative x between 0 and 2. Using right endpoints, find a limit, or an expression for A as a limit. Do not evaluate the limit. Everybody's good with the direction? So the two things we need to find the value for delta x and our expression for our arbitrary x coordinate that we'll be plugging into our fx. Okay? The formula for delta x is b minus a over n. My a and b are just the start and end of my interval. Since we're using right endpoints, my xi is going to be, where did you go? There. It's going to be this guy, a plus I times b minus a over n, or delta x, you could write it that way also. I'm going to try not to use the delta x's. The textbook loves to do it because it's less writing and it's easier to type format it. I'm going to write b minus a over n in almost every situation because that's the way you want to think about it, because you don't want to like have to loop through a million different formulas. And they love to write like xi here rather than writing this all out. I'm going to write this part out when I do it every time because, again, I don't want to step through a second formula to get, you know what I mean? I don't want formulas nested inside of formulas, so I can just write it out the full way. Stop. Oh my God. I just broke life. Okay. Feel okay with what we've done? So this is just like 2 over n, and this is like 2i over n. So our formula is always the limit of the sum of delta x times f of xi. Because we're using right-hand limits, our xi is going to be 2i over n. And because our interval starts and ends at 2, our delta x is 2 over n. So it's just like, can you take the information and fill it into a formula? Well, I guess we could do a little bit better, right? Because we know what f of x is. F of x is a specific thing. It's e to the negative x. So I guess we should do that. Right. All I did was plugged 2i over n into the function in the problem, and f of x is equal to e to the negative x. That's probably the answer to the back of the book, if this was a back of the book problem. That feel okay. Again, it's just about getting comfortable with like, what is this representing, getting used to the summations. Where these little formulas come in, how do we use them to get the stuff to go there, what they're representing. The delta x is the base, the f of xi is the height. That's all that means. All right. Part B says estimate the area by taking sample points to be the midpoints and using 4 subintervals and then 10 subintervals. Okay, I'm just going to do it for 4 subintervals because if you can do it for 4, you can do it for 10. Would you agree? And maybe I'm going to drop the graph in here. I think I have the graph still. Nope. Oh yeah, because I did that. Where did you go? There you are. So I'm going to drop the graph in here so you can really see what I'm doing specifically now. Everybody okay? So we're going to deal with n equals 4. So the first thing I'm going to do is calculate my delta x. So I go from 0 to 2. So my delta x is 1. Okay? So my x0 is a, which is just 0. My x1 is a plus 1 times delta x, so 0 plus a half, so 1/2. My x2 is a plus 2 delta x, so that's 0 plus 2 times a half. 1, you get the picture at this point, right? So far, so good. Now, the directions say to use the midpoints to calculate the heights, right? So between 0 and a half, what's my midpoint? 1.25, right? Between a half and 1, the midpoint is 0.75. Okay. Between 1 and 1.5, 1.25. Between 1.5 and 2, 1.75. So those are my rectangles that I'm going to find here. Now, is it necessary that I draw this whole convoluted picture here? No. Once you get the gist of what's going on here, you do not need to draw this. The first time going through and doing this, please draw this. It helps enormously connect what's going on graphically and visually to what you're doing algebraically. Doing this the first time, you should draw the pictures to do these calculations. It'll nail everything down nice and tight. Things will go much, much better. Okay, so what are we going to do? My area is approximately 1/2 times f of 0.25 plus 1/2 times f of 0.75 plus 1/2 times f of 1.25 plus 1/2 times f of 1.75. Looks good. And remember, f is e to the negative x. And then it's just going to be calculator time. And I'm going to leave that to you guys as an exercise to function through the calc. Yes,
Would you be able to plug forward or add equation up that answer?
No, because that's going to use the right-hand endpoints. Here it has to use midpoints. So the values, what we would need to change is, yeah, this starting value, right? So it would have to be like, divided by 2 or something. Right, because it's the start. No, it'd be, yeah, we'd have to make an adjustment here. Yes, yeah. I think that, like, to make it work in general for midpoints, you'd have to be a little bit more careful than that. You'd probably do like plus, it'd be like 1.5 I times the step or something. Or no, 0.5 I times the step. Or something like that. We'd have to be careful about it though. But yes, I mean, like, ideally you want to write a new formula for a midpoint. But like, in general, if you're doing this for infinitely many things, the answer you get using midpoints or left hands or right hands, it's all going to be the same. If you're doing finitely many, you'll get a different answer, right? In this case, we did just 4. Does that feel okay? Everybody's okay? These are good questions, guys. And then I said I wasn't going to bother doing the 10 one because, like, yuck, it's a lot. Especially with as gross as the numbers are going to be with the e to the negative whatever. Last example says, suppose the odometer on our car is broken and we want to estimate the distance driven over a 30-second interval. We take speedometer readings every 5 seconds and record them in the following table. So we have speed and we're looking to recover distance from this. That's like doing an antiderivative. It's going to be the same as the area under the curve. Is okay? Do I have a specific function for this curve? No. So what I'm going to do okay. So I have like 0:17, 5:21, 10:24, 15:29, 20:32, 25:31, 30:28, and now I'm just gonna like build some rectangles. You know what I mean, guys? And if I really wanted to get the best estimate I could, I'd do the left-hand sums and the right-hand sums and take the average of them or something. Does that feel okay? So again, next time, homework quiz 5.1. It'll be similar to like that kind of a problem. Or just like, you know, like here's the stuff, can you get it into the limit form? And then we'll look at the next delta math, or I'm sorry, not next related rate set. For Sunday at midnight, it's just the 4.9 homework. And I think I might have asked for you to put the related rate 1 in there too. I can't remember. It's in minor ordained.
So we don't have to do this for Sunday?
This is not part of Sundays.
Okay.
You're welcome. You too. Take care, everybody.